Listening Practice, Chapter 1, Introduction to Land Surveying 1.1 History and Evolution of Surveying, Ancient Surveying, Egyptian Rope Stretchers, 3000 BCE, 4 Nile Flood, Roman agrimensaries with Groma instruments, 18th-19th century, Invention of the theodolite, 1787, Great Trigonometric Survey of India, 1802-1871, Modern Era, Satellite Geodesy, GPS, 1978 plus, LiDAR and drone-based surveys, 21st century, boundaries 1.2 branches of surveying type scope precision example use. Geodetic large areas, considering Earth's curvature, high, plus or minus 1 mm/km, continental drift studies plain small areas, ignoring curvature, moderate residential subdivisions cadastral property boundaries legal grade land title surveys topographic natural/man-made features 1:500 1:5000 scale GIS base maps 1.3 applications in modern engineering, construction. Golden Gate Bridge, 1,280 m main span positioned with less than or equal to 50 mm tolerance, 1937, urban planning, Singapore's vertical city surveys for high-rise alignment, disaster management, LiDAR mapping of Fukushima exclusion zone, 2011, Key features timeline, from knotted ropes to quantum gravimeters decision tree, which survey type to use, flowchart case study, how erroneous surveys caused the 1846 dueling neighbors land conflict. Would you like to add, a comparison of ancient versus modern instruments? Ethics discussion on survey fraud cases. Emerging trends like AI-assisted boundary recognition. Asterisk, this chapter establishes surveying's historical context while highlighting its critical role in contemporary projects. Chapter 2, Basic Measurement Concepts in Land Surveying 2.1 Units and Conversions Fundamental Units, Linear, Meter, SI, Foot, Imperial, Angular, Degrees Minutes Seconds, DMS, Radians, Gradians, Area, Hectare, 10,000 square meters, Acre, 43,560 feet. Superscript 2, Critical Conversions, from to multiply by example --1 chain, Gunters, feet 66 2 chains equals 132 feet 1 mil, NATO, degree 0.056256 6400 mils equals 360 degrees. 1 square rod square meters 25.29294 rod. Superscript 2 101.1716 square meters. Field tip, always verify unit settings on instruments, e.g., total stations switching between metric/imperial. 2.2 Accuracy, precision, and errors. Key definitions: accuracy, closeness to true value, e.g., GPS versus tape measure; precision, repeatability, e.g., EDM versus pacing; error types, error class cause mitigation systematic instrument calibration regular adjustment, e.g., level collimation, random environmental factors multiple measurements blunders human mistakes field verification. Procedures industry standard tolerances, property surveys, 1:10,000, 1 cm per 100 m, construction staking, plus or minus 3 mm for high-rise columns. 2.3 Significant figures and error propagation. Significant figure rules: 1 All non-zero digits are significant. 2 Leading zeros never count. 3 Trailing zeros after decimal are significant. Example, 12.300 m has 5 sig figs, implies plus or minus 0.0005 m. Precision, 0.0045 degrees has 2 sig figs. Error propagation formulas: 1 addition/subtraction, \sigma_a plus or minus b equals \sqrt \sigma_a2 plus \sigma_b2 \2 multiplication, \frac \sigma_above equals \sqrt left, \frac \sigma_aa right, 2 plus \left, /frac sigma underscore bb /right, 2 field scenario, calculating area of 50.0 m plus or minus 0.1 m times 30.0 m plus or minus 0.1 m, nominal area equals 1,500 square meters, uncertainty equals plus or minus 0.1 superscript 2 plus 0.1 superscript 2, equals plus or minus 0.14 m per side plus or minus 4.2 m superscript 2 in area chapter tools conversion cheat sheet, laminated field card template error identification game, spot the blunder in sample field notes case study, the 1825 Mississippi bubble land scam due to measurement fraud. Discussion topics: how does GPS multipath error demonstrate random vs systematic effects? Why does thermal expansion of steel tapes require correction formulas? When should surveyors round intermediate calculations vs final results? This chapter equips surveyors with the quantitative rigor needed for reliable measurements while acknowledging real-world imperfections. Chapter 3, Surveying Mathematics 3.1 Coordinate Geometry Key Concepts, Cartesian versus Polar Coordinates, Cartesian, x, y, z, for mapping, polar, distance, angle, for field measurements, coordinate transformations, local to state plane conversions, Helmert transformations for datum shifts critical formulas, 1 distance between points, \d equals \sqrt, x underscore 2, x underscore 1, 2 plus, y underscore 2, y underscore 1, 2 \2. Bearing calculation, \theta equals \10 minus 1 left, \frac x underscore 2, x underscore 1 y underscore 2, y underscore 1 right, \quad, text adjusted for quadrant, practical example, converting total station measurements, slope distance, zenith angle, to 3D coordinates. 3.2 Trigonometry for surveying essential applications, 1 Triangulation, solving missing side/angles in control networks, using law of sines for inaccessible points, \frac a \sin a equals \frac b \sin b equals \frac c /sin c 2. Traverse calculations, latitude equals L-cos, departure equals L-sin, balancing misclosure errors field technique, intersection/resection, using angles from known points to locate new stations. 3.3 Area and volume calculations area methods, method when to use formula DMD, double meridian distance, closed traverses \a equals \frac 1 2 \sum underscore I equals 1 n, x underscore I, y underscore I plus 1, y underscore I, x underscore I plus 1, \Simpson's rule. Irregular boundaries \a equals \frac d3 y underscore 0 plus 4 y underscore 1 plus 2 y underscore 2 plus y underscore n \volume calculations, 1 end area method, for linear projects \v equals \frac a underscore 1 plus a underscore 2 2 times l \2. Prismoidal formula, higher accuracy \v equals \frac l6, a underscore 1 plus 4 a underscore m plus a underscore 2, real world accuracy, cut/fill volumes for 1 km highway project typically plus or minus 2-5% of actual chapter tools coordinate conversion worksheet, local left and right arrow state plane left and right arrow UTM, traverse adjustment spreadsheet template field cheat sheet, quick trig solutions for common scenarios, volume error estimation table case studies, how incorrect coordinate transformations caused a 15 m error in a pipeline project, why the 1858 lost corner survey dispute resulted from arithmetic mistakes. Discussion topics, when to use grid versus ground distances in state plane coordinates, how GPS elevation errors affect volume calculations, pros/cons of automated coordinate geometry, COGO, software. This chapter transforms mathematical theory into practical field tools, emphasizing the computational precision required for legal and engineering surveys. Chapter 4, Linear measurement methods in land surveying. 4.1 Chain surveying. Traditional technique, uses Gunter's chain, 66 feet/100 links, or metric chain, 20 m/30 m, components, arrows, pegs, ranging rods, accuracy, 1:1000, 0.1% of measured length, field procedure, 1 ranging, aligning measurement lines with ranging rods. 2. Chaining, stretching chain taut with uniform tension. 3. Booking, recording measurements in field book. Common errors and corrections, error type correction formula --slope \l equals l /dot /cos temperature c_t equals alpha, tt_0, l /sag c_s equals \frac w2 l324 p2 modern adaptation, steel tapes with tension handles for higher precision, 1:5000 accuracy, -4.2 electronic distance measurement, EDM, working principle, phase difference measurement of modulated infrared/light waves, typical range, 15 km, prism dependent, key specifications, parameter typical value accuracy plus or minus, 2 mm plus 2 ppm, measurement time 0.53 seconds, prism constant -30 mm to +40 mm. Field best practices, avoid measurements during high refraction, midday heat, regular reflectorless mode calibration, account for atmospheric corrections, ppm settings, -4.3 total stations integrated system. Components, 1 EDM, plus or minus 1-3 mm accuracy, 2. Digital theodolite, 1 to 5 arcsecond resolution, 3. Data collector advanced features, automatic target recognition, ATR plus or minus 0.5 pointing accuracy, robotic operation, single operator surveying, 3D scanning, up to 1 million points/hour field workflow, 1 setup, tripod leveling, bubble within 1, 2. Orientation, backside to known control point. 3. Topography, shoot points at 10-20 m intervals. 4. Staking, upload design points for construction layout accuracy comparison, method relative accuracy best use case ---- chain surveying 1:1000 rural boundary surveys EDM 1:10,000 control network extension total station 1:50,000 high precision construction chapter tools chain survey checklist 10-point verification before measurement EDM error budget calculator atmospheric/target/ instrument errors total station maintenance schedule case studies, how a 2 degrees Celsius temperature variation caused 8 cm error in a 1 km pipeline survey, why the Golden Gate Bridge used INVAR tapes for critical measurements emerging trends, ultra-wideband, UWB, for indoor surveying, quantum EDM prototypes, sub-mm accuracy at 10 km, this chapter bridges traditional techniques with modern instrumentation, emphasizing error awareness throughout the measurement process. Chapter 5, Angular Measurement Instruments in Land Surveying 5.1 Theodolites and Their Uses Fundamental instrument, measures horizontal and vertical angles with telescopic sight, key components, alidade, upper rotating assembly, horizontal and vertical circles, leveling base with foot screws. Types of theodolites, type reading system accuracy typical use ---- optical vernier / micrometer scale 10 to 20 arcsec traditional construction digital electronic encoder 1 to 5 arcsec precision control networks field applications, establishing traverse networks, triangulation for control point extension, alignment surveys, tunnels, bridges, -5.2 digital theodolites technological advancements, absolute encoders, instant angle display, no zeroing required, dual axis compensation, automatic tilt correction, plus or minus 3 range, data output, RS-232 or Bluetooth. Connectivity operational features, Function benefit face left / face right eliminates instrument errors. Repetition mode increases angular measurement precision. Laser plummet faster. Setup over optical plummets. Field procedure example: 1. Setup over point with tripod leveled, bubble within 1 division. 2. Side backside with 0 degree 0000 set as reference. 3. Turn angle to foresight, e.g., 45 degrees 30 minutes 20 seconds. 4. Repeat on opposite face, FL/FR, to eliminate collimation error. 5.3 Measurement of horizontal and vertical angles. Horizontal angle measurement: 1. Direction method: site reference target at 0 degree 0000, turn and record angle to target, e.g., 127 degrees 45 minutes 30 seconds. 2. Repetition method: for higher precision, measure angle multiple times and average, reduces pointing errors by n equals number of repetitions. Vertical angle measurement: zenith angles, 0 degrees at zenith, 90 degrees at horizon. Dip correction: \text corrected equals \text observed plus 0.067 times \sqrt \text dist km degree \error. Sources and corrections: error type correction method collimation, line of sight, FL/FR observation. Averaging horizontal axis tilt dual axis compensator activation vertical index error 0 check before observations chapter tools theodolite calibration checklist weekly/monthly tests angle measurement field sheet template error propagation calculator for multi-angle traverses case studies how a 12 collimation error caused 30 cm offset in a 500 m tunnel alignment, why the Paris Meridian arc required 7-year angular measurements 1792 to 1799. Practical tips: always use shade umbrella for precision work to avoid thermal drift. Force centering systems reduce setup errors to 0.1 mm. Record temperature during observations for refraction analysis. This chapter provides both the mechanical understanding of angle measurement instruments and the procedural rigor needed for geodetic quality work. Chapter 6: Leveling instruments and techniques. 6.1 Dumpy levels and auto levels. Dumpy levels: optical levels, components, telescope with fixed focus, no internal focusing lens, 4 leveling screws for precise adjustment, sensitivity, 20 to 30 arc seconds per 2 mm division. Advantages: rugged construction for field use, no batteries required. Limitations: manual bubble leveling required before each reading, slower operation compared to auto levels. Automatic levels. Key features: compensator mechanism, plus or minus 15 self-leveling range, magnification, 24x to 32x, striding level for quick setup verification, field efficiency, 40% faster observations than dumpy levels, typical accuracy, plus or minus 1.5 mm per km, double run leveling. Instrument comparison feature: dumpy level, auto level leveling method, manual automatic setup time 2 to 3 minutes 30 to 60 seconds, best for rough surveys. Precision work cost $200 to $500, $800 to $2,500. 6.2 Differential leveling field procedure 1. Setup: instrument midway between BS and FS points, max 50 m sight lines. 2. Readings: backside, BS, to known BM, 2.135 m, foresight, FS, to new point, 1.872 m. 3. Calculation: high equals BM elevation plus BS equals 100.000 plus 2.135 equals 102.135 m, new point elevation equals high, FS equals 102.135 to 1.872 equals 100.263 m. Accuracy standards: survey class closure tolerance application first order plus or minus 3 kmm, K equals km, geodetic control third order plus or minus 12 kmm. Construction projects: common errors: collimation error, eliminated by equalizing BS/FS distances, rod settlement, Use turning plates on soft ground. Refraction, avoid measurements during temperature inversions. 6.3 Profile leveling and cross-sectioning. Profile leveling, purpose, elevation data along linear projects, roads, stationing, 50 m intervals for preliminary surveys, 10 m intervals for detailed design. Field notes. Example: station BS high FS elevation remarks dash 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 0 plus 0 0 1.205 100 and 1.205 100.000 bm number 32 0 plus 50 1.872 99.333 center line. Pipelines, cross-sectioning, methods, grid method, 5m times 5m grids for small areas, radial method, from center line at 90 degrees offsets, volume calculation, and area method, V equals L times, A plus A, /2, typical accuracy, plus or minus 5% for earthwork quantities. Practical applications. Construction case study, project, highway grade control, technique, running levels every 50 m with 3-wire leveling, result, achieved plus or minus 5 mm vertical control over 2 km alignment. Emerging technologies, digital level systems. Barcode staff reading, e.g., Leica DNA03, plus or minus 0.3 mm/km accuracy, GPS leveling, ellipsoid to orthometric height conversion, requires local geoid model corrections. Field checklist. Verify instrument calibration every 6 months. Use INVAR rods for first order leveling. Maintain less than or equal to 30 m sight distances in turbulent conditions. This chapter bridges traditional leveling techniques with modern practices, emphasizing the precision required for elevation control in engineering surveys. Chapter 7, Modern Surveying Equipment and Techniques. 7.1 GPS and GNSS Technology. Global Navigation Satellite Systems, GNSS, Constellations, GPS, USA, 31 operational satellites, GLONASS, Russia, 24 satellites, Galileo, EU, 26 satellites, Beidou, China, 35 satellites. Survey grade GNSS receivers. Type accuracy. Typical use case RTK GNSS 8 mm plus 1 ppm H/15 mm plus 1 ppm V. Cadastral surveys, construction. Staking PPK GNSS 5 mm plus 0.5 ppm H/10 mm plus 1 ppm V. Aerial mapping, offshore surveys. Network RTK 10 to 20 mm. Real-time large area topographic surveys. Field workflow. Example 1. Base station setup, known coordinate point with radio link to rover operation, 30-second occupation per point, RTK, 3. Quality control, check PDOP, 3, and satellite count, 12. 7.2 LiDAR surveying system components, airborne LiDAR, pulse rate, 50 to 2000 kHz, accuracy, 5 to 30 cm vertical, density, 1 to 50 points/m. Superscript 2, terrestrial LiDAR, range, 0.5 m 2 km, scan speed, up to 2 million PTS/SEC. Data products. Output application digital elevation model, DEM, flood modeling. 3D point cloud structural deformation monitoring. Intensity image. Utility detection. Case study, project, highway corridor mapping, equipment, Regal VQ1562 airborne system, result, 500HA mapped at 20 PTS/m. Superscript 2 in 3 flight hours. 7.3 drones in surveying UAV platforms. Comparison. Type endurance payload capacity best for fixed wing 60 to 90 minutes 0.5 to 2 kilograms. Linear infrastructure multi-rotor 20 to 40 minutes 1 to 5 kilograms. Site inspections VTOL 45 to 75 minutes 1 to 3 kilograms. Mixed missions photogrammetry workflow 1. Flight planning, 80% side lap, 70% end lap at 100 MAGL 2. Ground control, 5 to 10 targets per 50HA, RTK verification, 3. Processing, accuracy, 1-3 times GSD, e.g., 3 cm GSD 3 to 9 cm accuracy, outputs, orthomosaics, DSMs, contour lines regulatory considerations, FAA Part 107, USA Max Altitude 120 MAGL, VLOS Operation, EASA Regulations, EUA 1/A3 Operator Certificates - Technology Integration Hybrid Survey Example 1. GNSS, Establish Ground Control Points 2. UAV, Capture High-Res Imagery, 1 cm/pixel, 3. Mobile LiDAR, Scan Vertical Structures 4. Total Station, Verify Critical Dimensions Accuracy Comparison Method Relative Accuracy Cost per Hectare GNSS RTK 1 to 2 cm $50 to $100 UAV Photogrammetry 2 to 5 cm $20 to $50 Airborne LiDAR 5 to 15 cm $100 to $300 Emerging Trends, AI-powered processing, automatic feature extraction from point clouds, quantum GNSS, centimeter accuracy without base stations, experimental, swarm mapping, multiple autonomous drones. Surveying simultaneously field checklist verify GNSS base station radio link, 450 to 470 MHz, conduct LiDAR system boresite calibration monthly maintain UAV battery log, replace after 200 cycles, asterisk. This chapter demonstrates how modern equipment revolutionizes surveying efficiency while maintaining geospatial accuracy requirements. Asterisk Chapter 8, Traverse Surveying 8.1 Open and Closed Traverses Types of Traverses Type Characteristics Applications Accuracy Check -- Closed Traverse starts and ends at known points Property Boundaries Angular Misclosure less than or equal to 5 n/arcsec Open Traverse ends at unknown point Route surveys no geometric closure Loop Traverse returns to starting point. Misclosure less than or equal to 1:10,000 Control Networks Linear Field Setup Requirements, minimum 3 known control points for orientation, maximum traverse leg length, urban areas, 150 m, rural areas, 500 m. 8.2 Traverse Computations and Adjustments Computation Steps 1. Angle Adjustment, distribute angular error equally, / text correction equals / frac / text total misclosure / text number of angles / example, 30 error over 5 angles plus 6 / angle 2. Coordinate calculation, latitude equals L times cos, azimuth, departure equals L times sin, azimuth, 3. Bow ditch adjustment, proportional distribution of linear misclosure, / text correction _ x equals / frac / text total error _ x times / text leg length / text perimeter / accuracy standard survey class angular closure linear closure -- first order 3 n/arcscans 1:50,000 third order 15 n/arcscans 1:10,000 8.3 Coordinate systems and transformations Common coordinate system projection scale factor. Use case -- UTM transverse Mercator 0.9996 Continental Survey State Plane Lambert / Mercator 1.0000 plus or minus 0.0001 Legal Boundary Surveys Local Grid Arbitrary 1.0000 Construction Sites Transformation Methods 1. 2D Helmert Transformation, / begin bmatrix x / y / end bmatrix _new equals / begin bmatrix and b / b and a / end bmatrix / begin bmatrix x / y / end bmatrix _old plus / begin bmatrix t _x / t _y / end bmatrix / where a equals s / dot / cos / b equals s / dot / sin / 2. Grid to ground conversion, \text ground distance equals \frac text grid distance text combined factor practical applications case study, urban boundary survey, equipment, 1 total station with prismless EDM, traverse, 8-sided closed loop, 1.2 km perimeter, results, angular misclosure, 12, within 15 8 equals 42 tolerance, linear misclosure, 1:15,000 after adjustment common errors and solutions error source detection method correction prism constant mismatch baseline verification reobserve with correct PC atmospheric refraction morning/evening checks limit sights to 150 m instrument drift periodic backsighting adjust trib ratch calibration emerging technologies, automated traverse adjustment, cloud-based least squares solutions, blockchain for survey data, immutable record of raw observations, augmented reality, real-time traverse visualization on site field checklist verify instrument calibration before starting maintain minimum 3 redundant control points document atmospheric conditions hourly. This chapter provides the complete workflow for precise traverse surveys, from field procedures to computational adjustments, meeting both engineering and legal accuracy requirements. Chapter 9, Topographic Surveying 9.1 Contour lines and their properties definition and characteristics, contour, an imaginary line connecting points of equal elevation, key parameters, contour interval, vertical distance between contours, e.g., 0.5 m for engineering sites, index contours, every fifth line, bolded with elevation labels, properties of contour lines feature interpretation example close spacing steep slope cliff faces, 30 degrees gradient, wide spacing gentle slope floodplains, 5 degrees gradient, closed loops hills or depressions volcanic craters V-shaped patterns valleys, point upstream, river courses accuracy standards, Asper's class 1, vertical RMSE less than or equal to 1/2 contour interval, typical tolerances, urban areas, plus or minus 15 cm vertical, wooded areas, plus or minus 30 cm vertical. 9.2 Methods of contouring field techniques comparison method equipment density. PTS/HA, best for total station robotic TS and prism rod 50 to 200 small sites, 5 HA, GNSS RTK survey grade receiver 20 to 100 open terrain LiDAR airborne/UAV system 500 to 10,000 large areas with vegetation photogrammetry UAV plus 35 MP camera 100 to 1000 3D modeling grid method procedure 1. Establish 10 m times 10 m grid, adjust based on terrain complexity, 2. Record elevations at all grid intersections 3. Interpolate contours between points using \E_P equals E_A plus \frac D_1 D_1 plus D_2, E_B, E_A, \where D_1 equals distance to point A. 9.3 Preparation of topographic maps map components 1. Base information, coordinate grid, UTM/state plane, north arrow, true/magnetic/grid, 2. Topographic elements, contours, 0.25 mm line width, spot heights at critical points 3. Cultural features, buildings, footprint and elevation, roads, with center line grades, digital workflow 1. Data processing, TIN generation from survey points, contour smoothing, 0.5 m tolerance, 2. Symbolization, ANSI/ISO standard symbols, layer organization, e.g., vegetation, utilities, 3. Output formats, CAD, DWG/DXF, for engineering design, GIS, SHOP/GOTIFF, for spatial analysis case study, highway design survey, area, 8 km corridor, 150 m width, technique, UAV photogrammetry and GNSS control, deliverables, 0.5 m interval contours, plus or minus 10 cm accuracy, 200 plus cross-sections at 40 m spacing. Emerging technologies, AI-assisted feature extraction, automatic identification of cliffs, drainages, real-time topo mapping, GNSS rover with live contour generation, holographic displays, 3D terrain visualization in field offices. Quality control checklist. Verify 10% of survey points with independent method. Check contour consistency at map joins. Validate spot heights at critical features, e.g., bridge abutments. This chapter bridges traditional surveying techniques with modern digital workflows, emphasizing the role of topographic data in engineering design and land management. Chapter 10, Construction Surveying. 10.1 Setting out buildings and structures. Key principles, converts design coordinates. Physical markers on site, tolerance hierarchy, structural elements, plus or minus 3 mm, rough grading, plus or minus 50 mm. Standard procedure. 1. Plan preparation, extract key points from CAD, column centers, slab edges. 2. Field execution, radial stakeout using total station, 1 to 2 mm plus 2 ppm accuracy, batter boards for foundation control. 3. Verification, diagonal measurements, Pythagorean checks, special techniques, laser scanning, for complex steel structures, e.g., 0.5 mm accuracy on weld points, slope staking, cut/fill markings at 10 m intervals. Formula, \text slope ratio equals \frac \text vertical \text horizontal \10.2 Control surveys for construction network design. Control level spacing accuracy. Mark type primary 200-400 m plus or minus 2 mm plus 1 ppm. Deep driven monuments. Secondary 50-100 m plus or minus 5 mm. Epoxy bolts. Tertiary 10-20 m plus or minus 10 mm. Nail/washer sets. Monitoring considerations, frequency, weekly for high-rise, monthly for earthworks. Deformation thresholds, alert level, 10 mm movement, action level, 25 mm movement. Instrumentation, automated total stations, e.g., Leica TM60, in-place inclinometers, plus or minus 0.01 degree resolution, -10.3 As-built surveys. Critical elements. 1. Vertical structures, floor flatness, FF/FL numbers per ASTM E1155, column plumbness, less than or equal to H/500 tolerance. 2. Linear infrastructure, pipeline invert elevations, plus or minus 5 mm, road crown gradients, 0.5% verification, documentation standards. Discipline required accuracy. Deliverable format -- architectural plus or minus 10 mm PDF and Revit model. Mechanical plus or minus 5 mm point cloud, LA/LAS, civil plus or minus 15 mm GIS. Compatible surfaces. Case study, high-rise tower, technology, robotic total station plus 3D laser scanner. Findings, 12 mm. Northward tilt at 300 m height, 8 mm. Floor level variations, resolution, adjusted cladding panel dimensions. Digital workflow integration. BIM coordination. 1. Field to BIM, cloud upload of as-built point clouds, clash detection in novice works. 2. BIM to field, AR overlays for MEP installations. Emerging tools, blockchain verification, immutable record of survey checks, autonomous UGVs, for tunnel as-built mapping. Quality assurance protocol. 5% random remeasurement check. Cross-validate with independent system, e.g., photogrammetry versus TS, document all set-out points with timestamped photos. This chapter provides the complete construction survey life cycle, from initial stakeout to final verification, with emphasis on metrology grade. Precision for modern building projects. Chapter 11, Hydrographic Surveying. 11.1 Methods for measuring water depths. Depth measurement technologies. Method accuracy. Max depth. Best use case -- single beam echo sounder plus or minus 0.01 m plus 0.1% depth. 200 m channel maintenance surveys. Multi-beam sonar, MBES, plus or minus 0.02 m plus 0.2% depth, 11,000 m port construction LiDAR bathymeter plus or minus 0.15 m, up to 3 seki depth, 50 m coastal zone mapping. Critical corrections 1. Sound velocity profile, measured with CTD profiler, accuracy plus or minus 0.5 m/s, typical adjustment, 3 to 5% of measured depth 2. Tide compensation, real-time telemetry gauges versus predicted tides, NOAA benchmarks for vertical control. Case example, project, Panama Canal deepening, equipment, Kongsberg EM2040 MBES, 400 kHz, result, 50 m depth mapped at 5 cm resolution. 11.2 Shoreline surveys mapping techniques 1. Wet-dry line detection, UAV photogrammetry at 0.5 cm GSD, water index algorithms, NDWI. 2. Vertical datum connection, RTK GNSS on airboats, plus or minus 2 cm vertical, MHW, mean high water, determination erosion monitoring, annual change analysis, DSAS, digital shoreline analysis system, typical rates, 0.5-5 m/year, sandy coasts, regulatory compliance, NOAA nautical chart standards, 1:10,000 scale for harbor charts, all features 1 m must be shown. 11.3 Flow measurements velocity measurement methods instrument principle accuracy ADCP Doppler shift, 4 beams, plus or minus 0.5% discharge electromagnetic Faraday's law plus or minus 1% float method surface velocity times 0.85 plus or minus 15% discharge calculation /q equals /sum underscore I equals 1n, v underscore I /d underscore I /w underscore I, where, v equals velocity, m/s, d equals depth, m, w equals width, m, extreme flow surveying, flash floods, non-contact radar gauges, UAV-based surface velocimetry, tidal bores, 10 Hz sampling rate ADCPs integrated hydrospatial workflow data. Fusion example 1. MBES, riverbed morphology 2. LiDAR, bank topography 3. Thermal cam, subsurface spring detection emerging technologies, autonomous USVs, Kongsberg Hyojin for 24/7 surveys, quantum gravimetry, detecting underwater cavities safety protocols dual frequency systems for shallow/deep transitions 30% overlap on MBES swath spare transducer arrays for emergency replacement. This chapter combines traditional hydrographic techniques with cutting-edge sensors, addressing the unique challenges of aquatic environments from rivers to deep ocean surveys. Chapter 12, Geodetic Surveying 12.1 Earth's Shape and Size Considerations Reference Ellipsoid semi-major axis, M, flattening, 1/f, used in WGS 846,378,137.0 GPS GRS 806,378,137.0 N 88 Clark 1866 6,378,206.4 294.978698214 N 82 7 Geoid modeling, EGM 2008, 1.5 resolution, 5 cm geoid undulation accuracy, local geoids. GEOID 18, USA plus or minus 1.5 cm continental accuracy, AUS Geoid 2020, plus or minus 3 cm over Australia. Practical implications, ellipsoid versus orthometric height, \h equals h, and \quad \text, h equals orthometric, h equals ellipsoidal, n equals geoid height, \, deflection of vertical, up to 50 in mountainous regions. 12.2 Coordinate systems. Latitude/longitude formats. Format example precision decimal degrees 34.052235 degrees north, 118.243683 degrees west, 0.000001 degrees 11 centimeters. Degrees minutes seconds 34 degrees 0308 n, 118 degrees 14 minutes 37 seconds west, 130 MUTM. Zone characteristics, 6 degrees longitudinal zones, 60 total, false easting, 500,000 m, scale factor, 0.9996 at central meridian, latitude bands, 8 degrees increments, cx, excluding IO, coordinate transformation. Example 1. Input, N88 state plane, California Zone 5, U.S. survey feet. 2. Steps, convert to meters, 1 U.S. survey foot equals 0.304800696 m, apply N88 to WGS84 transformation, 3 parameter, project to UTM Zone 11 N-12.3 datums and projections. Horizontal datum types. Datum reference frame point of origin accuracy WGS84 global Earth center of mass ±1 m. NAD83, 2011, Continental 3 US/CAN/MEX core stations ±2 cm. ED50 regional Potsdam, Germany ±5 m. Common projections. Projection preserved property distortion at zone edge transverse Mercator angles 0.04% scale Lambert conformal shapes 0.05% area Albers equal areas 2 degrees angular grid convergence calculation \\gamma equals \arctan \10 lambda_0 \sin \where \lambda_0 equals central meridian longitude, typical values, 0.5 degree 3 degree within UTM zones. Modern geodetic techniques. GNSS cores networks, NGS cores, 2,100 plus stations in USA, 1 Hz data, processing, PPP, precise point positioning 2 to 5 centimeters accuracy, network RTK, 1 to 2 centimeters relative positioning. Gravity surveys, absolute gravimeters, FG5X, 0.1 gal accuracy, applications, subsidence monitoring, 1 gal 3 mm elevation change, mineral exploration case study, continental drift monitoring, equipment, 12 GNSS permanent stations, findings, Pacific plate moving NW at 8.3 cm/year, annual adjustment of NAD83, MA11. Coordinates - field procedures and quality control. Datum transformation checklist. 1. Verify source/target APSG codes, e.g., APSG 4326 for WGS84. 2. Apply correct epoch, e.g., ITRF 2014 at epoch 2020.0. 3. Check transformation residuals, 5 cm for 3 parameter, emerging technologies, VLBI, quasar-based position control, ±1 mm intercontinental, quantum positioning, cold atom gravimeters for underground mapping. Common errors to avoid mixing ellipsoidal and orthometric heights without geoid model. Applying 7 parameter transformations without sufficient control points. Using deprecated datums, e.g., N827 for new surveys. This chapter provides the mathematical foundation for high precision. Geospatial positioning, bridging theoretical geodesy with practical surveying applications. Chapter 13, Cadastral and Legal Surveying. 13.1 Property Boundary Surveys. Boundary Determination Hierarchy. 1. Original monuments, highest authority, iron pins, stone markers, ±0.03 m. Recovery tolerance, witness trees, forensic dendrochronology verification. 2. Plat dimensions, meets and bounds descriptions, angular precision ±30, subdivision plats, scale 1 equals 100 minimum. 3. Possession evidence, fence lines, 20 years adverse possession, agricultural patterns, please section corners, surveyor's legal liability, standard of care, title research, minimum 40-year chain, 100% monument search within 5 m of theoretical, typical errors, 12% of retracement surveys find 0.5 m discrepancies. 13.2 Land registration systems, global systems comparison, system type, countries, accuracy requirement, digital coverage. Torrens, title, Australia, Canada, plus or minus 0.02 m plus 50 ppm, 98% deeds recording, USA, UK varies by jurisdiction, 35 to 75% cadastral parcel, Germany, Sweden, plus or minus 0.10 m, 100% blockchain applications, smart contracts, auto-triggered boundary updates, fraud prevention, immutable transaction history, pilot projects, Georgia, country, 1.5 m parcels on blockchain, Honduras, 60% reduction in title disputes. 13.3 Easements and right-of-way surveys, easement types, type, typical width, survey requirements. Utility 3-10 m as built versus design, plus or minus 0.10 m access, 5-20 m center line stakeout every 15 m conservation, 3300 m biophysical feature mapping, railroad row case study, project, high-speed rail corridor, challenges, 19th century deed ambiguities, 83 encroaching structures, solution, LiDAR corridor mapping, plus or minus 0.05 m, 3D. Volumetric easement models. Legal survey workflow, boundary conflict resolution. 1. Evidence weighting, original monuments, 50% weight, fence lines, 30%, tax parcels, 20%. 2. Court standards, U.S., Brown's Boundary Principles, UK, Law of Property Act 1925, Emerging Technologies, AI deed interpretation, NLP for historic documents, AR boundary visualization, real-time parcel overlay, drone monument search, multispectral detection of buried markers. Professional ethics, maintain 2:1 evidence ratio for boundary adjustments, disclose all conflicting evidence, 3% discrepancy, archive field notes for minimum 15 years. This chapter bridges surveying precision with legal doctrine, emphasizing evidentiary chain of custody in boundary determination processes. Chapter 14, Mine Surveying. 14.1 Underground survey techniques, instrumentation for underground work, tool, accuracy, depth, range, use case, gyro, theodolite, plus or minus 20 arcscans, unlimited shaft plumbing, scanning, total station, plus or minus 3 mm at 50 m, 500 m, stope mapping, borehole probe, plus or minus 0.1 degree inclination, 2,000 m, deep vein tracking. Specialized methods, shaft plumbing, 2-wire method. 1:50,000 accuracy, centering targets every 100 m depth, spiral traverses, 30 m maximum leg lengths, force centering, trib rocks, laser scanning in mines, point density, 1000 pts/m. Superscript 2 for stability analysis. Challenges, dust mitigation, requires forced air cleaning, limited GPS availability. 14.2 Volume calculations for mining ore body modeling. 1. Triangulation, tin, 5 m spacing for open pit, 1 m spacing for high-grade veins. 2. Kriging estimation, variogram analysis for optimal weighting. Volume computation methods. Method error range best for cross-section plus or minus 7% long, narrow deposits. Inverse distance plus or minus 5%. Isolated ore bodies. Block model plus or minus 3%. Large-scale operations. Production reporting, dilution factors, typically 5 to 15%, ore/waste classification, cut-off grade determination, tonnage factors, m superscript 3 tons conversion, dash. 14.3 Safety considerations. Hazard monitoring systems. 1. Microseismic arrays, 50 Hz sampling rate, 5 m event location accuracy. 2. Convergence meters, 0.01 mm resolution, alert thresholds, 2 mm/day, warning, 5 mm/day, evacuation, ventilation surveys, anemometry, vane anemometers, plus or minus 0.1 m/s, traverse method for airway sections, gas detection, methane, 0 to 100% LEL, CO, 0-500 ppm, emergency preparedness, escapeway mapping, updated weekly, 10m interval stations, self-contained self-rescuers, 60-minute oxygen supply, placement every 200m. Integrated mine survey workflow. Digital mine integration 1. Real-time data flow, survey planning production, 15 minutes delay max. 2. Automated alerts, wall movement 10 mm triggers drone inspection. Case study, deep copper mine, challenge, 1,200 m depth, 50 degrees Celsius rock temps, solution, robotic total stations with cooling jackets, fiber optic deformation monitoring, outcome, 99.8% survey data reliability, 0 survey-related incidents in 5 years. Emerging technologies, boring automation, autonomous drill guidance, plus or minus 2 cm, gravimetric or tracking, 10 gal sensitivity sensors, AI hazard prediction, 85% accurate fall of ground forecasts. This chapter combines traditional mining survey methods with cutting-edge monitoring technologies, emphasizing the critical role of precise measurements in both resource optimization and worker safety. Route surveying. Route surveying involves the planning, design, and construction of transportation infrastructure such as highways, railways, and canals. Key aspects include alignment selection, curve design, and earthwork calculations. 1. Highway and railway alignment. Alignment refers to the direction and position of a highway or railway in the horizontal and vertical planes. Factors affecting alignment: topography, minimizing cuts and fills, geology, stable foundation, traffic requirements, site distance, gradients, economic considerations, cost effectiveness, environmental and social impact, avoiding sensitive areas. Types of alignment: straight alignment, shortest path, but may not be practical; curved alignment, used to navigate obstacles, provide smooth transitions. 2. Horizontal and vertical curves. A horizontal curves used to change the direction of a highway or railway smoothly. Types: 1. Simple circular curve, constant radius arc. 2. Compound curve, 2 or more circular curves with different radii. 3. Reverse curve, 2 curves in opposite directions. 4. Transition, spiral, curve gradually changes radius, used in railways and high-speed roads. Key elements: radius, r, defines curve sharpness. Deflection angle, delta, angle between tangents. Tangent length, t, distance from PC, point of curvature, to pi, point of intersection. Length of curve, L, distance from PC to PT, point of tangency. B. Vertical curves used to provide smooth transitions between different grades, slopes. Types: 1. Crest curve, at a hilltop, convex shape. 2. Sag curve, at a valley, concave shape. Key elements: grade, G1, G2, slope before and after the curve. Length of curve, L, determines the rate of elevation change. K value, L/A, where A equals algebraic difference in grades, controls curve design speed. 3. Earthwork calculations. Earthwork involves calculating cut, excavation, and fill, embankment, volumes for road/railway construction. Methods: 1. Average end area method \V equals \frac A_1 plus A_2 2 \times L where A_1, A_2 equals cross-sectional areas, L equals distance between sections. 2. Prismoidal formula, more accurate, \V equals \frac L6, A_1 plus 4 A_m plus A_2, where A_m equals midsection area. 3. Borrow pit method, for irregular terrain, uses a grid to compute volume based on cut/fill depths. Applications, balancing cut and fill to minimize material transport. Estimating costs for excavation and embankment. Conclusion: route surveying ensures safe, efficient, and economical transportation routes by selecting optimal alignments. Designing smooth horizontal and vertical curves. Accurately computing earthwork volumes. Would you like a numerical example on curve design or earthwork calculations? Survey data adjustments. Survey measurements contain errors due to instrument limitations, environmental factors, and human mistakes. Adjustment computations refine raw data to produce the most probable values while minimizing discrepancies. 1. Least squares adjustment, LSA, the most rigorous method for adjusting survey data by minimizing the sum of squared residuals, errors. Key concepts: observations, L measured values, angles, distances, elevations. Residuals, V differences between observed and adjusted values. Weight matrix, P reflects measurement reliability, higher weight equals more precise. Types of LSA: 1. Parametric least squares, observation equations, directly models observations as functions of unknown parameters. Example, adjusting coordinates from multiple angle/distance measurements. 2. Condition least squares, condition equations, uses geometric constraints, e.g., closed traverse sum of angles equals, n2, times 180 degree. Steps: 1. Formulate the mathematical model, functional model. 2. Assign weights based on measurement precision. 3. Solve the normal equations, \n equals ATPA \quad \text and \quad t equals ATPL \x equals n-1t \quad \text, solution for unknowns, \4. Compute residuals and assess accuracy. Applications, adjusting control networks, traverses, GNSS baselines. Calibrating instruments. 2. Error ellipses, graphical representation of positional uncertainty for adjusted points. Components, semi-major axis, sigma_max maximum error direction. Semi-minor axis, sigma_min minimum error direction. Orientation angle, theta direction of sigma_max relative to the reference axis. Calculation, 1. Extract variance covariance matrix, sigma, for the point coordinates. 2. Eigen decomposition of sigma yields sigma_max, sigma_min, and theta uses, visualizing precision of control points. Planning additional surveys in weak network areas. 3. Network adjustments, process of refining measurements in interconnected survey networks, e.g., traverses, GNSS networks. Types: 1. Free network adjustment, no fixed constraints, minimizes distortions but requires a datum definition. Example, adjusting a GNSS network without fixed control points. 2. Constrained network adjustment, fixes some points/observations to a reference frame. Example, adjusting a traverse tied to known benchmarks. Steps: 1. Define network geometry, points, observations. 2. Assign weights, inverse of variances. 3. Apply LSA to solve for adjusted coordinates. 4. Analyze residuals and statistical tests, e.g., chi-square test for overall goodness of it. Outputs, adjusted coordinates. Standard deviations, precision. Error ellipses. Key formulas and examples. Least squares example, for a distance measurement \L equals 100.00 \text m with standard deviation \sigma equals 0.01 text m weight p equals 1 /sigma 2 equals 10,000 If residual v equals -0.02 text m contribution to the total error equals v2 times p equals 4 \. Error ellipse example, for a point with covariance matrix, \\sigma equals \begin b matrix 0.002 and 0.001 \0.001 and 0.003 end b matrix eigenvalues lambda underscore 1, lambda underscore 2 give sigma underscore max equals sqrt lambda underscore 1 and sigma underscore min equals sqrt lambda underscore 2 conclusion, least squares adjustment optimizes measurements for maximum reliability. Error ellipses quantify and visualize positional uncertainty. Network adjustments ensure consistency in large-scale surveys. Would you like a step-by-step numerical example for LSA or error ellipse computation? Cartography and map production. Cartography is the science and art of creating maps to represent spatial information accurately and effectively. Modern cartography combines traditional principles with digital technologies to produce maps for navigation, planning, analysis, and visualization. 1. Map projections. Since the Earth is a 3D sphere, representing it on a 2D surface, map requires projections, which introduce distortions in shape, area, distance, or direction. Types of map projections. Projection type. Properties. Preserved distortions. Common uses cylindrical, Mercator, direction, conformal, extreme area distortion. Near poles. Navigation, web maps, Google Maps, conic, Lambert. Conformal. Conic, shape, conformal, distortion away from standard parallels. Mid-latitude regions, USA, Europe, azimuthal, polar. Stereographic, distance and direction from center. Distortion increases outward. Polar regions, air routes. Equal area, Albers, mile wide, area, equivalent, shape. Distortion. Thematic maps, population, climate, compromise, Robinson, Winkle. Tripole, balanced distortions. Moderate distortion in all properties. World maps, National Geographic, selection criteria, purpose, navigation versus thematic analysis, region, polar, mid-latitude, global, required properties, shape, area, distance, direction, dash. 2. Symbolization and generalization. A symbolization maps use visual elements to represent real-world features, points, cities, landmarks, lines, roads, rivers, contours, polygons, lakes, countries, land use zones, colors, blue equals water, green equals vegetation, patterns and textures, hatching for swamps, stippling for deserts. Thematic map types, choropleth, shaded regions, e.g., population density, isoline, contour lines, e.g., elevation, temperature, dot density, dots represent quantities, e.g., population distribution. B. Generalization. Simplifying map details to improve clarity at smaller scales, simplification, smoothing river curves, aggregation, merging small forest patches, selection, omitting minor roads, exaggeration, emphasizing important features, e.g., highway width. 3. Digital mapping techniques. Modern mapping relies on GIS, geographic information systems, and automated tools. A. Data sources, satellite imagery, Landsat, Sentinel, aerial photogrammetry, drones, LiDAR, GNSS surveys, GPS, GLONASS, OpenStreetMap and volunteer geographic data, VGI, VGI's workflow. 1. Data collection, field surveys, remote sensing. 2. Data processing, georeferencing, topology correction. 3. Spatial analysis, buffer zones, network analysis. 4. Map design, layer styling, labeling. 5. Output, print maps, web maps, 3D visualizations, see web and mobile mapping, tile-based maps, Google Maps, Mapbox, interactive web GIS, ArcGIS Online, QGIS Cloud, Augmented Reality, AR, Maps, Real-Time Navigation Overlays, Conclusion, Map Projections Balance Distortions based on Purpose. Symbolization and Generalization enhance readability. Digital mapping integrates GIS, remote sensing, and web technologies. Need a deeper dive into a specific projection or GIS technique? Let me know. 18 Geographic Information Systems, GIS, for surveyors. Geographic Information Systems, GIS, integrate spatial data, coordinates, terrain, features, with attribute data, descriptions, measurements, to analyze, visualize, and manage geographic information. Surveyors play a crucial role in GIS by providing high-precision geospatial data for mapping and decision-making. 1. GIS Basics for surveyors. Key concepts: spatial data, represents real-world locations, points, lines, polygons. Attribute data, descriptive information, e.g., parcel owner, elevation. Coordinate systems, geographic, lat/long, WGS84, global positioning. Projected, UTM, state plane, flat maps for local surveys. Topology, ensures spatial relationships, e.g., parcels must not overlap. GIS software used in surveying. Software use case ArcGIS Pro, ESRI, Professional GIS Analysis, Municipal Mapping. QGIS, open source, free alternative for data processing. AutoCAD Civil 3D Survey Drafting, Terrain Modeling. Trimble Business Center. GNSS and Total Station Data Processing. 2. Data collection for GIS. Surveyors collect primary GIS data through field surveying methods. Method data collected: precision total station coordinates, elevations ±1-5 mm GNSS/GPS RTK real-time positioning ±1-2 cm, with corrections, LiDAR scanning 3D point clouds, topography, structures, ±2-5 cm drone photogrammetry orthophotos, DEMS ±3-10 cm. Secondary data sources, existing cadastral maps, property boundaries, satellite/aerial imagery, Google Earth, USGS, government databases, USGS DEMS, OpenStreetMap, data formats, vector data, points, survey markers, lines, roads, polygons, parcels. Raster data, elevation models, DEM, orthophotos. Common file types, shapefile, .shop, GeoJSON, DWG, CAD, LOS, LiDAR. 3. Surveying applications in GIS. Cadastral and land surveying, parcel mapping, legal boundary definitions. Subdivision planning, splitting land into lots. Engineering and construction, road design, horizontal/vertical alignment in GIS and Civil 3D. Volume calculations, cut/fill analysis for earthworks. Environmental and topographic surveys, flood modeling, using LiDAR-derived DEMS. Slope analysis, landslide risk assessment. Utility and infrastructure mapping, underground utilities, water, gas, and telecom networks. Asset management, tracking infrastructure conditions. Case study, GIS in survey workflow. 1. Field data collection, GNSS rover marks property corners. 2. Data processing, adjustments in Trimble Business Center. 3. GIS integration, import into ArcGIS for parcel mapping. 4. Analysis, overlay with zoning laws for development planning. 5. Output, interactive web map for stakeholders. Conclusion, GIS enhances surveying by integrating precise measurements with spatial analysis. Surveyors provide critical data for GIS, ensuring accuracy in maps and models. Applications range from land development to infrastructure management. Need a workflow example or software comparison? Let me know. 19. Surveying standards and regulations. Surveying is a regulated profession that requires strict adherence to technical standards, ethics, and legal requirements to ensure public safety, property rights, and professional integrity. 1. Professional ethics in surveying. Surveyors must follow ethical guidelines to maintain trust and credibility. Key ethical principles: integrity, provide honest, unbiased results. Competence, work within one's expertise, seek training when needed. Confidentiality, protect client data unless legally required to disclose. Public welfare, prioritize safety and environmental protection. Conflict of interest, avoid situations where personal gain conflicts with professional duty. Codes of ethics, examples: National Society of Professional Surveyors, NSPS, U.S. Standards. International Federation of Surveyors, FIG, Global Guidelines. State/country-specific boards, e.g., GNSS in the U.S. Violations can lead to license revocation, fines, legal action. 2. Licensing requirements. Surveying is a licensed profession in most countries to ensure only qualified individuals perform legal surveys. A U.S. licensing process, GNSS model. 1. Education, bachelor's degree in surveying/geomatics, or related field and coursework. 2. Fundamentals of surveying, FS, exam, entry-level test on math, geodesy, laws. 3. Work experience, 4+ years under a licensed surveyor, varies by state. 4. Principles and practice of surveying, PS, exam, advanced exam on legal boundaries, ethics, and practice. 5. State board approval, additional state-specific requirements, e.g., jurisprudence exam. B. International licensing, examples: Canada, provincial associations, e.g., OLS in Ontario. UK, chartered surveyor, RICS, certification. Australia, licensed surveyor, state-based registration. Continuing education, CE, most states require annual CE credits, e.g., 1530 hours, to renew licenses. 3. Liability and legal aspects. Surveyors face legal risks if errors lead to property disputes, construction failures, or financial losses. A common legal issues. 1. Boundary disputes. Incorrect surveys can lead to lawsuits over land ownership. Courts often rely on original plats and monuments. 2. Title insurance claims. Survey errors may void insurance coverage. 3. Construction errors. Faulty elevation data can cause flooding or structural failures. B. Risk mitigation strategies. Professional liability insurance, errors and omissions covers legal defense and damages. Written contracts, clearly define scope, accuracy standards, and limitations. Field notes and documentation, maintain records to defend against claims. Adherence to standards, follow ALTA/NSPS land title surveys, U.S., or local equivalents. See notable legal cases: Robinson v. Ladd, 1996 surveyor held liable for relying on an erroneous prior survey. Browns-Tyco v. Chicago title, 1985 surveyor's failure to mark boundaries led to costly litigation. Conclusion: ethics ensure professionalism and public trust. Licensing guarantees competency, education, exams, experience. Legal compliance minimizes liability risks. Need details on your state/country's licensing process? Ask for a breakdown. 20. Survey project management. Effective survey project management ensures projects are completed on time, within budget, and to required accuracy standards. It involves planning, field operations, and data handling to deliver reliable results. 1. Planning and cost estimation. A project planning steps. 1. Define scope, purpose, boundary survey, topographic mapping, construction, deliverables, CAD drawings, GIS files, legal descriptions. 2. Site reconnaissance, visit site to assess terrain, access, and potential challenges. 3. Select survey methods, GNSS RTK for open areas, total station for dense urban sites. LiDAR/UAV for large area topographic surveys. For risk assessment, weather, permits, underground utilities, wildlife hazards. Layout. B. Cost estimation, cost factor considerations labor crew size, hourly rates, overtime equipment rental fees, depreciation, calibration travel and logistics vehicle costs, accommodation for remote sites permits and fees municipal approvals, land access fees data processing software licenses, office labor example budget breakdown, field work, 60%, office processing, 25%, contingency, 15%-2. Field procedures. A. Pre-field preparation, equipment checks, calibrate total stations, GNSS receivers and levels. Verify backup batteries and data storage. Permits and permissions, secure landowner consent, municipal permits. Safety briefing, PPE, hard hats, high-vis vests, emergency protocols. B. Fieldwork execution task best practices control survey establish stable benchmarks for project control. Topographic survey capture key features, buildings, utilities, contours. Boundary survey follow deed descriptions, recover monuments. Construction staking verify design coordinates before marking. Common challenges and solutions, poor GPS signals. Use total stations in urban canyons. Missing monuments. Research historical records, use metal detectors. 3. Data management. A data collection workflow. 1. Field to office transfer, Cloud Sync, Trimble Connect, ArcGIS field maps. Redundant backups, external drives, cloud storage. 2. Data validation, check for gaps, outliers, or instrument errors. 3. Adjustments and processing, least squares adjustment for control networks. CAD/GIS integration, AutoCAD, QGIS. B. File organization, standard naming convention, projected _date _data type _user, e.g., Highway 2024 topo JSmith. Metadata documentation, coordinate system, equipment used, surveyor name. C. Deliverables output type format legal plats PDF, signed/sealed CAD drawings DWG, DXFGIS data shapefile, GeoJSON reports Word/PDF with methodology and findings case study, Highway Survey Project 1. Planning, ALTA survey standards, drone photogrammetry for slopes. 2. Fieldwork, RTK GNSS for center line, total station for bridges. 3. Data management, QA/QC checks before submitting to DOT. Key takeaways, plan meticulously to avoid delays/cost overruns. Follow field protocols for accurate, repeatable results. Secure and document data to prevent loss or legal issues. Need a project checklist or software recommendations? Ask below. 21 Emerging technologies in surveying. The surveying profession is undergoing a digital transformation, driven by cutting-edge technologies that improve accuracy, efficiency, and data visualization. Below are the latest advancements shaping the future of surveying. 1. 3D laser scanning, LiDAR and terrestrial laser scanning. How it works. LiDAR, light detection and ranging, uses pulsed lasers to measure distances, generating millions of 3D points, point clouds. Terrestrial laser scanners, TLS, capture high-resolution scans from ground stations. Applications. Industry use case construction as-built verification, clash detection mining volume calculations, slope stability archaeology digital preservation of heritage sites forensics crime scene documentation advantages high precision, level accuracy, fast data capture, minutes versus days with traditional methods, non-intrusive, safe for hazardous areas. Challenges, large data volumes require powerful processing software, e.g. AutoCAD recap, Cloud compare. Costly equipment, though drone-based LiDAR is becoming affordable. Dash 2. Augmented reality, AR, in surveying how it works, overlays digital survey data, BIM, GIS, CAD models, onto real-world views via smart glasses, Microsoft HoloLens, or tablets. Applications use case benefit construction staking visualize underground utilities before digging boundary marking see property lines in real-time on-site training virtual practice for surveying students example tools, Trimble Site Vision, AR for field surveys, Bentley Synchro XR, construction visualization, limitations, requires stable GPS/indoor positioning for alignment. Still in early adoption phases. Dash 3. Future trends in surveying AI and machine learning, automated feature extraction, e.g., AI identifies roads, buildings in drone imagery. Predictive surveying, AI forecasts land subsidence, erosion risks. B. Autonomous surveying drones and robots, self-flying drones with LiDAR/photogrammetry for large-scale mapping. Robotic total stations, e.g., Leica TS16 Auto-Lock, that track prisms automatically. C. Digital twins, real-time 3D models of infrastructure, bridges, cities, for monitoring. Used in smart cities and asset management. D. Blockchain for land records, tamper-proof land registries, piloted in Sweden, Georgia. Reduces fraudulent boundary disputes. Dash case study, Smart Highway Survey 1. LiDAR scanning captures as-built conditions of a highway. 2. AI processing detects crack patterns in pavement. 3. AR visualization engineers inspect issues via HoloLens overlay. 4. Digital twin monitors real-time deformation over time. Dash conclusion, 3D laser scanning equals high-precision reality capture. AR equals real-time data visualization on-site. Future tech equals AI, drones, blockchain will redefine surveying. Which technology interests you most? Want a deeper dive? Ask below. Appendices A, Surveying Formulas and Tables 1. Distance and angle calculations formula description slope distance horizontal distance HD equals SD times cos, theta, convert slope distance, SD to horizontal, HD using vertical angle, theta horizontal distance slope distance SD equals frac HD cos, theta, reverses the above calculation. Bearing to azimuth conversion text north 30 degrees east equals 30 degrees text south 45 degrees west equals 225 degrees converts quadrant bearings to azimuths, 0 degree 360 degree. 2. Traverse adjustment formula use latitude, delta y, equals L times cos, theta, departure, delta x, equals L times sin, theta, computes coordinate changes for traverse legs. Linear misclosure equals sqrt, sum delta x, 2 plus, sum delta y, 2 checks traverse closure error. Accuracy ratio equals frac 1, perimeter misclosure, expresses precision, e.g., 1:10,000. 3. Vertical curves, parabolic, y equals frac r2x2 plus g underscore 1x plus text elef underscore pvc r equals frac g underscore 2, g underscore 1l rate of change per station. G underscore 1, G underscore 2 equals initial/final grades, Dash B, Sample Survey Calculations Example 1, Traverse Adjustment given, legab, /L equals 150.00 / text M, / theta equals 45 degrees leg BC, L equals 200.00 / text M, / theta equals 135 degrees calculations, 1 lat / DEP for ab, / delta y equals 150 cos, 45 degrees, equals 106.07 / text M / delta x equals 150 sin, 45 degrees, equals 106.07 / text M 2 lat / DEP for BC, / delta y equals 200 cos, 135 degrees, equals minus 141.42 / text M / delta x equals 200 sin, 135 degrees, equals 141.42 / text M 3. Misclosure asterisk / sum / delta y equals minus 35.35 / text M / sum / delta x equals 247.49 / text M / text error equals /sqrt, minus 35.35, 2 plus 247.49, 2 equals 250.0 / text M adjustment, distribute error proportionally. -C, common surveying abbreviations abbrev. Meaning GNSS Global Navigation Satellite System RTK Real-Time Kinematic, GPS Correction, TBM Temporary Benchmark PLSS Public Land Survey System, US, DEM Digital Elevation Model GIS Geographic Information System LiDAR Light Detection and Ranging -D, Glossary of Surveying Terms Term Definition -- Azimuth Horizontal Angle from North, 0 degree 360 degree. Geoid Earth's true shape, used for elevations. Monument Permanent Survey Marker, e.g., iron rod. Orthophotogeoreferenced aerial image, no distortion. Staking marking construction points on site. References and further reading 1. Surveying Principles and Applications Barry Cavanaugh, Pearson. 2. Elementary Surveying Galani and Wolf, Pearson. 3. Manual of Surveying Instructions BLM, U.S. Bureau of Land Management. 4. NSPS Standards www.nsps.us.com, https://www.nsps.us.com. Need a specific formula explained? Ask for details. A comprehensive yet structured approach to land surveying. This guide is designed to serve as a complete yet organized resource for land surveying, catering to students learning core principles and techniques, practicing surveyors quick reference for fieldwork and calculations, engineers integrating surveying into civil/construction projects, GIS professionals handling geospatial data collection and processing. How this guide is structured. 1. Foundational knowledge, surveying basics, equipment, measurements, errors, coordinate systems and geodesy, datum, projections, transformations. 2. Field techniques, traversing and leveling, open/closed loops, adjustments, GNSS/GPS surveying, static versus RTK, error sources, topographic and hydrographic surveys, contours, bathymetry. 3. Computational methods, distance/angle corrections, slope, temperature, sag, least squares adjustment, network analysis, error ellipses, earthwork and volume calculations, end area, prismoidal. 4. Specialized surveying, construction surveying, staking, alignment, as-builts, cadastral and boundary surveys, deed research, legal principles, route surveying, highways, railways, vertical curves. 5. Modern technologies, 3D laser scanning, LiDAR, point cloud processing, drone/UAV surveying, photogrammetry, accuracy standards, augmented reality, AR, in surveying, Trimble sight vision. 6. Professional practice, licensing and ethics, NSAs, NSPS standards, project management, cost estimation, data workflows, legal aspects, boundary disputes, liability. Why this approach works. Modular design. Jump to relevant sections without reading linearly. Theory and practice formulas paired with real-world examples. Tech integrated covers both traditional and emerging methods. Audience-focused tailored insights for students, pros, and engineers. Example workflow, highway construction survey 1. Planning, ALTA standards, drone LiDAR scoping. 2. Fieldwork, RTK GNSS centerline, total station for bridges. 3. Processing, CAD drafting, earthwork volume calcs. 4. Delivery, GIS integration for Get the most from this guide, students, master fundamentals with sample calculations. Surveyors, use quick reference tables, formulas, abbreviations. Engineers, apply construction staking and as-built techniques. GIS pros, leverage GNSS data integration with ArcGIS/QGIS. Need a specific topic expanded? Ask below. Tip: bookmark the appendices for fast access to formulas and abbreviations.